Right, we're going to create reduction formulae, formulas, whatever the plural of formula is. Sometimes called a recurrence. So you might see that word used as well, sometimes recurrence formula. Basically, it's usually when you've got the integrand is to some power. And it saves you doing the same process over and over and over again. Trig, you see it in a lot. You know, those trig integrals when you're doing, say, like cos to the power of 5, but in order to do 5, you had to do 3 and things like that. So integration by parts is often used to find the formula. Don't be fooled into thinking that you have to do parts every single time, though. And they're not always by parts, but it is surprising how often we do integration for parts for these. So, okay, let's start with this little question. We're going to find the integral from 1 to e of x log x all cubed. Now, this one I would use parts to solve this question, but I'm going to create a formula. Okay, so in I'm going to call it, and instead of power of 3, I'll just call it power of n. So I'm sort of generalising the integral so I can solve it for any power of log. So my u will be log x to the power of n. My du will be n log x to the power of n minus 1 over x. dv becomes x, so v is a half x squared. We get uv half of x squared log x to the power of n minus v du. So half's a common factor, n is also a common factor we can pull out, and we get x log x to the n minus 1, and you can see we've reduced the power of the integral by 1. So we now have, there is, a little formula we can use to save us having to repeatedly integrate that log x to the power. You can now just go, righto, here's a formula I'm going to use. So essentially I want to find I3 then. So using my formula, I can say, well, I3 will be e squared on 2 minus 3 on 2 I2. But now I can use the formula to find I2. So I2 would be e squared on 2 minus I1, tidying that up. But now I'll find I1. Well, I1 will be e squared on 2 minus a half I0. Now I can't use the formula for I0, but it's certainly simplified the integral I now have, because it'll be log x to the power of 0. Well, anything to the power of 0 is 1. So our integral is now just integral of x dx. We still had to integrate, of course, because we integrated by parts to get that formula. But as I say, just saved us having to do it repeatedly. And integrate x, we get a half x squared. Subbing in, we eventually get our answer. Another way of using the reduction formula, see, here I've reduced. Some people like to build it up rather than reduce it down. So they start with I0. They say, well, I0, integral from 1 to e of x dx. So that's I0. And then they build it up and say, well, look, I1 would be I squared minus half I0. Sub in the answer I just got for I0. I2, sub in the answer we just worked out for I1, and I3, which is the one we want to work out for, sub in the answer for I2. It doesn't really matter, I suppose, whether you want to build it up or reduce it down. At the end of the day, you just need to get the final answer. So, integration by parts is that a word, commonest? Is the commonest way of getting it. But as I say, it's not the only method. You can get away with trig identities. Cot to the power of n. Remember, when we were doing tan and cotan, we used the same technique regardless of the power. So we'll just use that technique. We won't use integration by parts. So in we want to find. So cot to the power of n. If you remember, the technique was pull out a cot squared. You change the cot squared to cosec squared minus 1. And we split it up into 2 new integrals. The first one we can do via a substitution. U equals cot x. So du is minus cosec squared x dx. And the second one, I've reduced the power. So it becomes I n minus 2. Well, the integral of u n minus 2, I can add 1 to the power over the power. Sub back in for u. There's my formula. So I'll have minus 1 on n minus 1, cot n minus 1 minus I n minus 2. Another idea. When you're dealing with trig, because so many trig identities, the powers vary by 2. So you could try either adding or subtracting depending on which trig ratio you're working with. So it'll work for this one. If I go in plus 2 and actually add those two things together, I get cot n plus cot to the power of n plus 2, which I then can factorise the 1 plus cot squared, and that's why I did plus rather than minus for this one, because the trig identity is 1 plus cot squared, becomes the cosec squared, because we're dealing with the complementary ratios here. And I've got cot to the power of n cosec squared, which I can integrate. Let's just add 1 to the power over the power, because it's in the form derivative times function. And I've now created the formula, because I've got in plus 2 is that. So rearranging it, I get the same formula. So that often is a way you can play with trig ones to do it. Alright, so it's I6 that we want to find. So however we got the formula, we're now going to use it. I6 will be minus a fifth cot to the power of 5 minus I4. I4, well that's minus a third, but minus minus becomes a plus. And so now it's plus I2. I2 becomes minus cot to the power of 1 minus I0. Can we use this formula for 0? No, because we'd reduce it down to negative 2 and that's not going to work. So we'll actually work out I0, which is just the integral of dx, because cot to the power of 0 would be 1. Well, integrate dx, we get x, plus of course a constant. They don't always use integration by parts. Sometimes you have to do more than just integration by parts. Algebraic manipulation we see a lot in these integrations. So they've given us that in is 1 plus x squared to the power of n. We want to find a reduction formula, but they've given us a little bit of a hint. It'll end up connecting in with in minus 1. So we'll reduce by 1 each time here. Okay. So in is 1 plus x squared to the power of n. Well, I'm going to start off with parts, because as I say, a lot of them are done by that way. So if I let u equal 1 plus x squared to the power of n, to u, 2nx, 1 plus x squared n minus 1, to v is dx, v is x. So we get uv minus the integral of v du. Ooh, it's not quite the in formula, is it? Because I've got the x squared out the front. So this is where the algebraic manipulation comes in handy. So I rewrite the x squared as 1 plus x squared minus 1. Because then I can split that into two integrals. But both of them now become 1 plus x squared to the power of something. And that's what our formula is, 1 plus x squared to the power of something. So the second one is 1 plus x squared to the power of n. So that's in. And the last one there is 1 plus x squared to the n minus 1. So that's in minus 1. Now we want to just get a formula. If I move my in's to the left-hand side, I get 2n plus 1 lots of in. Divide by the 2n plus 1, and we have a wonderful formula there for reducing the 1 plus x squared to the power of n. All right, let's look at some actual ones that have appeared over the years. This 1987, quite a long time ago now. So it's cos. Now, unfortunately, we don't use the same technique each time with cos. Depending on whether it's odd or even, the technique we'd use, and they're just calling a power of n. If they made a power of 2n, it'd be great, because I know it's an even number. I could use that technique. N, I don't know. But they have given me the formula, so I know where I'm heading. And then we'll go and use it to find power of 5. So all right, there's in. I'm going to split it. I'm going to take a cos out and then do it by parts. So u is cos n minus 1, to u is minus n minus 2, etc., etc. To v becomes cos x, v is sin x. So we get uv. Now that's a nice one, because when you substitute pi on 2 into that one, the cosine is going to become 0, when you substitute 0 into that one, the sign's going to become 0. So all of that becomes 0. I'm left with the n minus 1 cos n minus 2 sine squared. I'd like to get cos to the power of something. So if I change my sine squared to 1 minus cos squared, then I can break that up into two integrals. 1's to the power of n minus 2, 1's to the power of n. I can create my formula now. So that's going to be n minus 1 I n minus 2 minus n minus 1 I n. Move the in's to the other side, and we have our answer. In is n minus 1 on n I n minus 2. However, they gave me the answer. So I could have tried something else. Again, because it's trig, differ by 2. So let's try plus or minus. In this case, it's cos. So I'm probably going to go 1 minus cos squared, 1 minus sine squared. So I'll try minus. So I n minus 2 minus I n. Let's see what happens. If I sub that in, I get cos n minus 2 minus cos n, which I can factorise straight away. I get the 1 minus cos squared, which is the sine squared. Well, use sine x to u is cos x. Notice I've still got to use parts. So did it save me time? Don't know. The square brackets there, the substitution, that becomes 0 again. I've got 1 on n minus 1 cos to the n, which is 1 on n minus 1 in. Was that quicker, you reckon? Oh no, we still had to do by parts. Yeah. But we come up with the answer. That's another way we can try it. Okay, we have to work out I5. Sub in I5, I get 4/5 I3. Sub in for I3, I get 2/3 I1. I1 is the integral of cos x. Integrate cos, we get sine. Sub in, and there's our answer, 8/15. Now, the nice thing, I guess, about these questions in the HSC is they usually tell you the formula you're heading to. So that way, even if you do muck up the first bit, at least you can go and get some marks and work out the integral using and show, well, I know how to use the formula. 2004, this was a beauty. I thought I'd share this one with you because I'm sure you'll love it. In is the integral for tan to the power of n, and jn. So we've actually got two different patterns here. Jn is going to be minus 1 to the power of n times I2n. We have to show, first of all, that in plus 2. So they're even telling us, don't muck about. Use the idea of in plus 2 to get this relationship. So if I substrate in, we can factorise and get the 1 plus tan squared, which gives us the sec squared. And so that's just a straight, well, if you don't see the derivative times function, we can do u equals tan x. And we end up with, there it is, 1 on n plus 1. Okay, so it was kind of nice of them to write it that way so we could get the answer. Part B. Deduce then that jn minus 1 is this lovely expression. Right, remember they defined in for us and they've defined jn for us. Jn was minus 1 to the power of n, I2n. So therefore jn minus 1 will be minus 1 to the power of n minus 1, I2n minus 2. Okay. Well, minus times minus gets me the minus 1 to the power of n, so at least I've got a common factor of minus 1. I'm just keeping an eye on where I'm heading to, so I've got the factor of the minus 1 to the power of n there. I've got that bit. So I to the 2n plus I to the 2n minus 2, I've somehow got to get this down. Well, hang on. In part A, if I let n equal 2n minus 2, I've got it. And so it was 1 over, subbing in for n 2n minus 2, I get the 2n minus 1. Okay, wasn't as bad as it immediately looked. So Jm, we're going to show is pi on 4 plus the sum of n equals 1 to m of that fraction. All right. Well, Jm is minus 1 to the power of m over 2m minus 1 plus Jm minus 1. Where did he get that from? Well, that's just a rearrangement of what we just proved. I've just moved the Jn minus 1 to the other side. And instead of an n, I'm using an m. All right, so we've got that. But hang on, I could use that formula again then and say Jm minus 1. So everywhere I see an m, I'm going to replace it with an m minus 1. So it becomes minus 1 m minus 1 on 2m minus 3 plus Jm minus 2. Hang on, I could use that formula again now. And wherever I see an m, I'm going to replace it with an m minus 2. And I could keep going and keep going and keep going. And then eventually I would reduce it to a point where I'd get J0. Okay. Well, so essentially, all of these terms here are in fact the sum that they're talking about. We go from 1 to m of minus 1 to the n on 2m minus 1. And all I'm left with is this little integral dx from 0 to pi on 4. And if we do that, we end up with pi on 4. And that's what they're looking for. But wait.
There's more.
There's more. Okay. We're now going to use the substitution u equals tan x to show that in actually is the same as this expression. Okay. Remember in, they told us, was the integral from 0 to pi on 4 of tan to the power of n. They've told us use this substitution. So u equals tan x. Another way of thinking about that is x equals the inverse tan of u. I'm thinking about it that way because it's going to make this substitution a lot easier. Rather than trying to get du in there, because look what happens with my x. I get dx is du on 1 plus u squared. I can just sub straight into my integral here. Yes, I've got to change the limits. So all right, when x equals 0, u equals 0. When x is pi on 4, u is 1. But it falls out straight away. So that's sometimes handy. Even though they've given me the substitution u equals, changing it to x equals, so then I can just substrate in for the dx, can save me some time. There's in. Wow. Deduce then that in is always between 0 and 1 on n plus 1, and then from there we will conclude that Jn must approach 0 as n approaches infinity. Okay. Well, the 0 bit's easy. U to the power of n on 1 plus u squared must be positive for any u that is positive. And if you look at our integral, we're going from 0 to 1, so we are always using positive numbers. So all right, we know that integral will always be positive, showing it's less than 1 on n plus 1. All right. Remember this? Back to this formula. in plus 2 was 1 on n plus 1. Well, that means in is 1 on n plus 1 minus in plus 2. But remember we just said that the in is always positive. So in is always 1 on n plus 1 minus some positive amount. Well, it must be less than it then. Bingo. We got the right-hand side of our inequality there. So, okay, in is in between 0 and 1 on n plus 1. But remember, that wasn't all they asked us to do. So what is the limit? Well, we could do that limit. The limit of 1 on n plus 1 is 0. Hang on. As n approaches 0 then, in is in between 0 and 0. So I know the limit as n approaches infinity of in is 0. That, of course, wasn't, if we go back to the question here, what they asked us what happens to Jn. Okay. Well, Jn was minus 1 to the power of n of I2n. So if in's going to 0, then Jn's going to 0 as well. All right, so I thought I'd show you that one because I think that's one of the more fun, well, I call it fun. I mean, you might have other words for it, I suppose. We do there.